Hello, everyone, and welcome to session 2 of the Mars 2020 Launch Educator Conference. Thank you for joining us today. If you registered for this event, you received an email with a link to ask questions. So feel free to enter your questions and upvote the questions that are already there during today's program. Today, our special guest is Matt Smith. Now, Matt and I have never actually met in person, but we've talked a bit over video conferencing, and I've got to know him a little bit. I think you're in for a really, really good program today. Matt is an engineer on the Mars 2020 mission and knows the ins and outs of how the rover works from an engineering perspective and some of the engineering finesse that goes into entry, descent, and landing. So Matt, I'm going to let you take it away from here.
Well, great, Oda. Thanks so much. And I'm really glad to be here and share some information about the NASA's next Mars rover, Perseverance. So we can jump right into the first slide here. This is a picture of Perseverance's older sister, I guess you could say, the Curiosity rover. It landed back in 2012. And this is a picture actually taken by the rover itself. It's kind of an interplanetary selfie that was acquired using the robotic arm at the end of the rover. And what I love about this picture is that you can really see the beautiful Martian landscape. Curiosity is currently exploring Gale Crater, and you can see the rim of the crater on the top right. It's actually landed at the base of a mountain called Mount Sharp, and that you can see the top of Mount Sharp in the top left of this photo. And it's a beautiful desert Martian landscape, but also it shows us how unforgiving Mars is as an environment. And the Mars 2020 Perseverance rover is really an example of pretty extreme engineering to deal with this harsh environment. So what I want to do is talk about the Martian environment, what the rover is going to do, and then take a deep dive really to even look inside the rover to see how we engineer it to deal with this harsh environment. A few things about Mars. It's really cold, so the average surface temperature of Mars is negative 64 degrees Fahrenheit, and the coldest temperature it gets at night could be almost minus 200 degrees Fahrenheit. Also, Mars has a thin atmosphere. It's mostly carbon dioxide, but the atmospheric density is only about 1% of Earth's atmosphere. Also, as you know, Mars is very far away. So on slide 2, you can see a picture of Earth taken from Mars by Curiosity. This was a few hours after sunset on Mars, and the Earth is just a small dot in the distance. You could actually see it if you were on the surface of Mars and had pretty good vision. But Mars is extremely far away from Earth. The closest it gets to Earth is about 35 million miles, and at its furthest distance, it's about 250 million miles. And Earth was about 100 million miles away when this picture was taken. So that means that the Perseverance rover is really on its own. There's no one around to change the tire, bring you spare parts. It also means Perseverance is going to be really far from the sun too. So that has implications about how we power the rover. So all of that goes into how we design this rover to withstand this really harsh environment. So before diving into the engineering, I want to go to slide 3, which sort of summarizes the goal of the mission. Perseverance is all about looking for evidence of ancient microbial life on the surface of Mars. And that breaks down into 3 sub-objectives that are shown here. So in terms of geology, the rover has instruments to understand the geological record on Mars to look to see if the location that we landed shows direct evidence of minerals that could only form in the presence of water and other geologic processes that maybe indicate the presence of life in the past. The second objective is astrobiology. So the Perseverance rover has instruments that can detect the chemical byproducts of ancient life potentially. And then the last objective related to finding ancient life on Mars is sample caching. And we'll get into that a bit more, but the Perseverance rover is really the first leg of a round trip to Mars, where this rover will be collecting samples on the surface and then storing them for retrieval by a future mission that would come later in the 2020s. One last thing is that the Perseverance rover is also laying the groundwork for human exploration of Mars. There's an instrument on board called MOXIE, which is going to extract oxygen from the Martian atmosphere. And you can use that for breathing, of course, but it's also useful for generating rocket fuel on the surface of Mars. So we'll talk a bit about that too. I want to talk quickly about the landing site for the Perseverance rover, and that's shown on slide 4 here. This is Jezero Crater, and this is where we're going to be going. It's about 45 kilometers wide, and the landing ellipse for Perseverance is shown there in the black circle. And at this view, it looks like a pretty typical crater. It's round, it has a crater rim and a depression. But if we zoom in closer to the landing site on slide 5, you can see a pretty interesting feature, and this is what really got the scientists excited about landing in Jezero Crater. So in that inset, you can see what looks like a dry riverbed on the left, upper left, and then emptying out into what looks like a river delta. So scientists think that 3 to 4 billion years ago, a river flowed in this region and emptied out into the Jezero Crater. And this is incredibly exciting because on Earth, everywhere we find water, we also find life. NASA has adopted a follow the water approach to looking for life elsewhere in the solar system, and the Jezero Crater is a prime place to look. This ancient water could have collected and preserved ancient signs of microbial life. So that's really why we're going to this specific spot on the surface of Mars. So the next slide, slide 6, shows what the rover looks like. This is a drawing of the rover, and it calls out the different instruments on board the rover. We have a really capable suite of instruments to help us characterize the geology of our landing site and look for those signs of ancient microbial life. We have RIMFAX, which is a subsurface radar that'll actually penetrate the ground on Mars and map out geological conditions underneath the surface. We have 3 instruments that are called out on top of what looks like the head of the rover. That's called our remote sensing mast. We have Mastcam-Z, which will give us these nice 3D panoramic images, and it has a zoom feature, which is new. SuperCam is a laser that can actually fire at rocks from a distance and can detect the chemical signatures of those rocks using that laser from a distance. META is a weather station on Mars, so every lander and rover we send has a weather station, so we can start to characterize the climate on Mars. Also, it's helpful for determining the wind speeds, things like that. At the end of the robotic arm, we have 2 really cool instruments, Pixel and Sherlock. Those are what are called spectrometers, and those can help us sniff out the chemical and elemental makeup of the rocks that we're looking at. There's also a drill on the end of the robotic arm that can collect rock samples to transfer into the rover as part of its caching subsystem. Finally, there's Moxie. Moxie is really cool. It's a tech demo. This is part of that preparing for humans on Mars, and it's going to extract oxygen from the Martian atmosphere to prove that we can do it. It's a challenging aspect of going to Mars. So if you tune in on July 7th, you'll hear a lot more about the instruments from my colleague, Christina Hernandez. I want to focus on the engineering behind getting those instruments to the right place on Mars, and that's shown on slide 7. So we have a mobility subsystem. That's kind of like the legs of the rover, getting it around next to targets that are interesting. We have a telecommunications subsystem. These are the radios that act like the ears and mouth of the rover to get commands from the Earth and to send data back to the Earth. We also have a power subsystem. It's kind of like the heart and cardiovascular subsystem. It provides energy to all the components on the rover. And then we have avionics. Avionics is just a fancy aerospace engineering term for computers and electronics. And that's sort of the brain and nervous system of Perseverance. So I want to dive into all these different components so you can see how we engineer them to deal with the surface of Mars. On slide 8, you can see the power supply for the Perseverance rover on the left there. It's called an RTG. That stands for radioisotope thermal electric generator. And inside that cylinder is about 10 pounds of plutonium dioxide that's slowly decaying, and that decay creates heat, and that heat is turned into electricity that powers the rover. The excess heat is also kind of nice because it keeps the rover toasty on those really cold Martian nights. On the right-hand side, you can see where the RTG is going to attach to the rover. We're kind of looking at the back of the rover, and there are 2 fins that stick out, and the RTG sits in the middle of those fins. It only generates about 110 watts, which is kind of the equivalent power of like 2 laptops. And that's not a ton of power to drive a 1,000 kilogram rover. So there are batteries on board also that store that power and then use it for driving or other things. Every night, the rover actually goes to sleep and turns off all of its components, including the computers, to save energy while the RTG is powering the batteries and charging up. So speaking of computers and electronics, I want to show you the inside of the rover on slide 9. We call this the belly of the beast, and it shows you all of the electronics that are packed into that rover body. Importantly, we have computers that serve as the brain of the rover. And notice I said computers, plural. There are actually 2 identical computers on board the rover, and they're really almost 2 identical components of every single item in the rover that's critical to its functionality. And the idea is that it gives you redundancy in the case of something going wrong. So you're on Mars, you're maybe 200 million miles from Earth. There's no AAA there to come and help you change your tire or swap out a broken part. So all that equipment really needs to be reliable, and you always have to have a backup. All of these things here communicate with Earth. So there are actually 3 different radios inside the rover. And that brings us to the telecommunication subsystem. So this is the eyes and ears of the rover. And Mars is interesting. It's actually a planet where we have satellites there already that can help us communicate with the rovers that we send. And it's a pretty cool feature of going to Mars. We have this relatively robust communication network that helps us. And that is shown on slide 10. So this is a great visualization of what we call the Mars Relay Network. It's that network of orbiters that helps us communicate with the rovers on Mars. You can actually go to that website there to explore this visualization yourself. And what it'll do is it shows you in real time where the orbiters are in relation to the different landers on Mars. And Perseverance will use these orbiters to send data from the surface up to orbit around Mars, and then the orbiters send data from the orbit of Mars to Earth. And we do that because the orbiters have a lot more power and a lot larger antennas than the smaller rovers on the ground. So the short distance between the rover and the orbiter on Mars is relatively easy to deal with. And then the orbiters can just blast that data back to the Earth, where it's received by huge radio dishes called the DSN. I've shown a picture there of our 70-meter DSN dish out in Goldstone, California. They're really massive antennas designed to listen to spacecraft at the very, very far reaches of the solar system. Perseverance will be able to talk directly to Earth in the event that there's not an orbiter overhead. But we think that most of the data will come back through the orbiter relay process that you're seeing here in this visualization. So go to that URL, you can check it out. It's really neat tool. The last part about the rover engineering that I want to talk about is the mobility subsystem. These are the wheels and suspension and the motors that drive us on the surface of Mars. And so the easiest thing to do would be to take a look at the video I have on slide 11. So this is a video of the first time Perseverance drove at JPL. We're in the clean room, and you can see everyone wearing their protective bunny suits to keep the rover clean. Perseverance has 6-wheel drive, so each wheel has its own drive motor, and you can see the rocky bogie suspension system. This actually allows the rover to drive over obstacles as big as the wheels themselves. There are 4 steering motors as well, so there are steering motors in the back 2 wheels and the front 2 wheels, and that lets the rover turn in place if needed. You might notice that the wheels on Perseverance look a little different than the wheels on Curiosity, and that's because the Curiosity wheels have experienced some damage over the years on being on Mars. It's part of that really harsh environment that has abraded the wheels a bit. So we redesigned the wheels for Curiosity. Really cool. We think they'll do a great job. So talked about some of the subsystems within the Perseverance rover, how we deal with the harsh environment of Mars, the fact that we're far away. Let's talk about how we put that all together and build it and test it. So slide 12 shows how this rover is packaged up for its flight to Mars and entry into the Martian atmosphere. It's kind of like a high-tech Russian nesting doll. So the rover, you can see there labeled, it sits underneath the descent stage, and we'll get into what the descent stage does in a second, but it's responsible for lowering the rover carefully onto the surface of Mars. The rover and descent stage together are encapsulated by the heat shield and the aeroshell, and those protect the rover and descent stage as the vehicle is flying through the Martian atmosphere extremely fast and generating a lot of heat. Then on the back of that, you have the cruise stage, and that is what makes this whole thing a spacecraft able to travel almost 300 million miles from Earth to Mars over the 7-month cruise period. I like to say that Perseverance is also kind of like a transformer. It starts out as a spacecraft and then converts to something like an aircraft that actually flies itself through the Martian atmosphere, then to a hovercraft, and then finally to a wheeled rover. So we'll see more about that transformation when we talk about the entry, descent, and landing process in a bit. So slide 13 shows a real picture of the actual flight hardware all ready to go. So on the very top there, you have the cruise stage. You can see some of the propellant tanks. The red cluster on the right is actually a set of thrusters that have covers on them for protection. Underneath the cruise stage, you see that back shell, and then you can see the rover tucked up in there. You can see a couple of the wheels. If you look really carefully, you can see some of the descent stage engines peeking out. And then at the bottom, you have that heat shield. So that whole thing has now been encapsulated, and the next time those pieces separate will actually be in the Martian atmosphere when we're about to land in February of 2021. So that's pretty cool. There's a lot of work that goes into preparing the vehicle, testing it, thousands and thousands and thousands of hours over many years. And slide 14 has a video that we can look at to show a little bit about that process. So we're here back in the JPL high bay. And this is showing the process of stacking up the spacecraft and getting it ready for testing. It's important to test everything in a similar environment to what we'll see on Mars. So we took the spacecraft up to a thermal vacuum chamber at JPL in a different building. And that chamber simulates the harsh temperature and pressures that the vehicle experienced on the way to Mars and at Mars. Then we took the vehicle back to the high bay and did a bunch of checkouts of the rover subsystems, like the remote sensing mask, that thing that pops up, the mobility subsystem that you learned about, the drill, the robotic arm. And you'll notice that everyone is wearing these white bunny suits, and that's to keep the rover clean while we prepare it for the journey to Mars. We don't want to accidentally have any germs on Earth that could stow away on the rover and give us a false detection for life once we're there. So we can go on to slide 15 and kind of recap where we're at. So we selected that Jezero crater landing site, talked a little bit about designing, building, assembling the rover. Next up is launch, and that's coming up right around the corner. July 20th is the start of our launch period. Then we are going to cruise to Mars. That's a 7-month period where we fly from Earth to Mars. We're going to land on February 18th, 2021, and then start our service operations. So as I mentioned, it all starts with launch. And slide 16 shows some pictures of our launch vehicle being prepared for the mission. These were just taken a couple weeks ago. The upper left shows how the launch vehicle is assembled. The launch vehicle is just a fancy word for the rocket. The Perseverance spacecraft sits on top of that vehicle inside what we call the payload fairing, or a nose cone. And that protects the spacecraft as the rocket is launching through the atmosphere of Earth. We discard it as we get high enough where the atmosphere won't damage the spacecraft anymore. But what really strikes me about these photos is how huge the rocket is. In the bottom left there, you can see people next to the base of the rocket, and they're just super tiny compared to this massive launch vehicle. It's over 190 feet tall, and it weighs over 1 million pounds when it's fully loaded. So that's pretty incredible. Slide 17 shows the Curiosity launch, and you'd expect a similar scene when Perseverance launches. So our first opportunity is on July 20th around 6:15 a.m. Pacific time, so definitely tune in for that. And the launch window runs until August 11th. Because of the alignment between Earth and Mars, we have opportunities to send things to Mars roughly every 26 months. So that's why we have this opportunity in 2020, and we really, really want to make this opportunity so we don't have to wait another 26 months to launch this rover. It takes about 7 months to get to Mars, and the whole trip is around 309 million miles. So during that time, we're going to be checking out the different instruments, other pieces of equipment to make sure we're all ready for entry, descent, and landing. We'll also be steering the spacecraft on a trajectory that puts us exactly where we need to be to do that landing. It's sort of like trying to hit a hole-in-one from California with a golf ball or a golf course in New York. It's a really delicate process of nudging the vehicle to the right spot at the right time. We're going to do entry, descent, and landing, or EDL, on February 18th, 2021. It's one of the most exciting and nerve-wracking parts of the mission that definitely required some extreme engineering. So I have a video on the next slide that shows you why, so we can start that up. The first thing that happens is that the crew stage is jettisoned from the vehicle. So at this point, we're flying through the atmosphere at about 12,000 miles per hour when we hit the top. That velocity causes a huge amount of friction, and the heat shield will reach temperatures of up to 1,600 degrees Fahrenheit. There are little thrusters on the aeroshell that actually steer the vehicle through the Martian atmosphere. We call this guided entry. We're actually flying the vehicle to the intended touchdown point. So once we're inside the atmosphere, we're still going over 900 miles per hour. So we deploy a supersonic parachute to slow down. It inflates in under a second and imparts about 9 Gs of force. So it's a really violent deceleration. So once the heat shield has done its job, we're inside the atmosphere, it falls away to expose the landing radar and the landing vision system. So the Martian atmosphere is too thin to slow down all the way with the parachute. So we actually detach from the back shell and fly away on rockets. We call this powered flight. And the descent stage is cool. It has a new camera system for Mars 2020 that will be used to pick out safe landing locations. This approach is called terrain relative navigation. And it lets us land the rover in locations that might be more hazardous than we would be able to achieve without that system. But those locations, even though they're more hazardous, they're more scientifically interesting. So the landing vision system takes pictures of the ground, and it can steer the descent stage to a safe location if it detects a hazard. This is what I call the hovercraft phase of the transformation of Perseverance from a spacecraft to a rover. So that landing vision system will help us select a safe spot for landing. Once we're about 65 feet over the landing location, the descent stage does what we call the sky crane maneuver. And the sky crane maneuver unspools the rover on a nylon bridle and gently lowers the rover onto its wheels on the surface of Mars. It's traveling just under 2 miles per hour at that point. So we've gone from 12,000 miles per hour down to 2 miles per hour over around 7 minutes during this EDL process. At touchdown, the bridle is cut and the descent stage flies off to crash land at a safe distance from the rover. So this is, to me, one of the most incredible parts of the mission, depositing this rover on its wheels on the surface of Mars after that 7-month cruise. So all of this has to happen automatically. On landing day, which again is February 18th, 2021, it'll take radio signals from Earth around 10 minutes to travel to Mars. So there's no way we could fly this spacecraft manually from Earth. Everything is programmed to happen without any humans in the loop. This all has to happen by itself. And in fact, it takes 7 minutes to get from the top of the atmosphere to the surface of Mars. And remember that light time is 10 minutes. So by the time we hear back that the spacecraft has landed, it will already have been on the surface for about 3 minutes. That just gives you a sense of how impossible really it would be to do with humans in the loop, and it has to take care of itself, all those intricate steps. So from there, the surface mission can start. We deploy the remote sensing mast, the robotic arm, do a bunch of other checkouts of the mobility system, and the mission itself will last at least 1 Martian year, which is 687 Earth days. So there's a lot of amazing science. There's a lot of really great technology demonstrations, including the Mars helicopter Ingenuity. That's a really neat thing that we're bringing along to the surface of Mars, the first helicopter on another planet. We're sure to learn all kinds of amazing things, thanks to some pretty extreme engineering here on the Perseverance rover. So that's all I have to share with you, but I'm happy to answer any questions we might have out there from members of the community.
Great, thanks, Matt. That was a really great overview of the engineering on the rover. And we do have a lot of questions. We have a good amount of time here for questions. We won't get to all the questions, but we'll get to as many as we possibly can.
Great.
So our first question is, what programming languages are used in writing Perseverance's software?
Good question. Okay. So all of the software on board the rover is written in C. And it's a very robust language. There's also other software though that we use to operate the mission. There's software on the ground systems that we use to develop our commands, and I think that software is written in Java, although I might have to double check that. And then in my job as a systems engineer, we do a lot of testing and data analysis. And for that, we use a lot of Python in our work. So it's kind of a mixed bag, but the software on the rover is C.
Okay, great. Thank you. Next question is, what skills are needed in order to have a successful engineering role at NASA?
It's another good question. So obviously, proficiency in math and science is really important as an engineer. Math is the language of engineering, and so it's pretty hard to get away from that. I think if you're an engineer, you probably like math and science a lot. Another skill I'd say is the ability to work as part of a team. So, this Perseverance rover is so complicated. It's taken so long to build, and it really is a huge team effort. Thousands of people have contributed to this really complex vehicle. And I think we're at the stage where truly groundbreaking science really requires a lot of collaboration. We're kind of gone from the days of a lone scientist sitting in a lab by themselves. These efforts really require big teams. So I'd say ability to work in a team is important. Also communication. We deal with really complicated discussion topics in our team meetings, trying to diagnose very challenging technical problems. And even with all these smart people in the room, sometimes just explaining the problem, just communicating can be a challenge. So I'm always impressed by my Mars 2020 team members with their ability to communicate really challenging technical questions and problems in a clear way.
That's an interesting piece of information for our teachers in the crowd who are not only teaching science and math subjects, but they're trying to also teach writing and speaking. And so it's good to hear that those things are also valuable. And of course, working with your teammates, so getting along and finding a way to work together. So that's
Absolutely.
Yeah, good to hear. Another question is, how do engineers design the rover to respond to the signal transmission delay from Earth to Mars? Does the rover have any autonomous capability?
Yeah, okay. The rover does have autonomous capability. So what usually happens is in the morning, we will send a bunch of sequences up to the rover, the Martian morning, that is. So before, like early morning on Mars, we'll send sequences up to the rover. And that's a list of instructions for what you're going to do today. And that can be pretty, what I'd say is like deterministic, right? It's just a list of things you need to do. But there are more sophisticated autonomous behaviors on board the rover. So for example, the rover does have an ability to drive itself several hundred meters, and it will use the cameras on board. There are actually, I think, around 23 cameras on the rover. Some of those are devoted to navigation, where the rover will take pictures. It has stereo vision, so it can determine where hazards are, and it will autonomously drive itself several hundred meters while also avoiding different obstacles that are in the way. Mars 2020 also has a feature on board called Onboard Planner, and that is a autonomy engine that helps decide how to trade off between different activities on board. And it's a new feature for 2020. So it's a good question. Yeah, we're so far away from Earth that really there are many cases where the rover just has to take care of itself and do all it can without human intervention. At the end of the day, then the rover will phone home and give us what it learned from that day's activities, and then while the rover's sleeping on Earth, we plan for the next day. That's kind of how it'll work.
Great, thank you. It's interesting. It's like it has some decision-making capabilities, so it can keep itself out of trouble, so to speak. So another question, how are the avionics insulated and protected from the extreme cold temperatures as well as from cosmic rays?
Okay, so there are a couple things going on. All the avionics reside in what we call the warm electronics box, and that's that belly of the beast picture you saw earlier. That box is insulated with advanced materials that there's something called aerogel that was developed at JPL. It's called liquid smoke. It's this very lightweight insulating material. So there's insulation in the rover. There's also a active thermal control system inside the rover. So there is, we talked about the RTG at the back of the rover, that thermoelectric power source that generates waste heat, and there's a thermal control loop that circulates fluid to basically keep all the electronics at a nice temperature using some of that waste heat. The question asked about cosmic radiation also. This is one of the reasons that Mars is a harsh environment, is because it doesn't really have a magnetic field the way that Earth does. That the Earth's magnetic field sort of gives us this protective bubble against the radiation that's flying through space. You don't have that on Mars, so the radiation environment is a lot higher than it is on Earth, and the electronics do need to be hardened against that. So there's a couple different ways that happens. One is just that the chips that we use in the rover are designed such that they can handle that radiation environment. Also, there's physical shielding that can block radiation, just bigger pieces of metal on top of the electronics to keep that radiation from getting to the chips that are sensitive to it. Also, we have different software on board that's monitoring for problems that could be caused by radiation. So that software, if it detects something, can actually clear it out, fix itself, and also phone back to the Earth to let it know that something's happened due to likely radiation.
Okay, great. It's really interesting. Another question here about sensors and instruments. Are there any sensors or instruments that scientists and engineers considered adding but ended up not putting on the rover? And if so, why were they eliminated?
Oh boy, that's a really good question. I actually don't have the answer. I know that the presentation in 2 weeks' time will have someone who is very familiar with the instrument selection and how all that went and what the instrument suite is. I will tell you that there was a very long process that took place over many years of soliciting instrument ideas, down selecting instruments, refining those ideas. So it's definitely a good question. There's a lot of interesting stuff there, I'm sure. I will touch on one thing though, which is the sample caching system. And remember, this is the first part of that round trip to Mars. Perseverance is going to collect samples to bring back to Earth during a later mission. And one of the reasons we do that is because it lets us, instead of bringing the instruments to Mars, it lets us bring Mars to Earth and use the full suite of instruments here, or maybe even invent new instruments that don't even exist yet. So that helps give us some flexibility to analyze these samples later on.
All right, sounds good. Yeah, our guest in the next program will be able to answer a lot more about the science instruments in particular, and she might have some insight on some of those intricacies of how things were decided for which instruments will go to Mars. It's like you said, a big process, and if scientists could have their way, they'd take every instrument probably, but there's only so much weight we can take with us. So our next question is about the helicopter. Will the helicopter be used one time only, or will it be reusable?
The helicopter is designed to do multiple flights during like a 30-day period on Mars. So yeah, we should talk about the helicopter a bit. It's called Ingenuity. It's really cool. It's it has two rotors that spin in opposite directions, and it looks kind of like a box on stilts. And this is a technology demonstration that Perseverance is taking with it to show that we can fly this vehicle on Mars. And who knows, if the helicopter works, maybe a future mission could use even bigger helicopter and go further. But the helicopter on Perseverance is designed to fly for about 90 seconds at a time, and it'll do that autonomously. It will land. It has a small solar panel that it'll use to charge its batteries. And once the batteries are charged back up, it can then hop again. So it'll do multiple 90-second hops over the course of the 30 days that it operates.
Yeah, it's an interesting technology demonstrator. If it works and everything goes as planned, that'd be fantastic for the future.
Yeah.
It was commonly believed that a helicopter could not fly in the extremely thin atmosphere of Mars. What did it take to design and engineer Ingenuity to demonstrate that belief was wrong?
That's a really good question. So it is a challenge to fly a helicopter in the Martian atmosphere. It's 1% the density of Earth's atmosphere. Um, so the helicopter was designed with, first of all, really fast blades. The helicopter's blades spin at about 2,400 RPM, which is a lot faster than a helicopter you'd see on Earth. Another thing is that it's extremely lightweight. So the blades are made using carbon fiber. The body and landing legs of the helicopter are very light. Also, so that was keeping the equipment on the helicopter to a minimum to minimize that weight was really important. And another part of it is the testing that went into proving that. So at JPL, we have this mantra, which is test as you fly, where we really try to test everything in a representative environment to get the sense that it will work before we send it up into space. So the helicopter team actually put the helicopter into one of those thermal vacuum chambers and pumped it down to the density that we expect on Mars. And they were able to show that it could fly in that environment, which gave us confidence that it will be able to fly on Mars once it gets there.
Yeah, so much like teachers who are trying to teach engineering concepts to students, the secret is testing and trying and revising and testing again and again. Yeah, so try to simulate the environment as best you can and then hope for the best upon launch.
Yep.
So next question is about communications.
Okay,
Are all communications stopped between the Mars rovers and orbiters when the sun is directly between Mars and Earth?
Yes. So the short answer is yes. We call that period conjunction, and it's when the sun is blocking our view to Mars, and it's about a 2-week period where all the Mars missions kind of go into this quiet mode during that time when it's difficult to communicate back and forth. So yeah, definitely we have to deal with the physics and geometry of the solar system in this job.
All right, very good. So here's a personal question for you. How did you develop your interest in engineering?
So I was always one of those kids that loved like Legos and model rockets and taking things apart and seeing how it worked. I also grew up in Pasadena, so I sort of grew up in the shadow of JPL and remember going there like in grammar school. I remember going to the high bay and seeing the Cassini mission. Cassini is a mission that went to Saturn, and it's one of the biggest spacecraft we've ever sent into the solar system. It's about 2 stories tall, and that trip really made an impression on me. I went on to study math as an undergrad, and kind of end of high school, early college. I wasn't exactly sure what I wanted to do. I mean, I always had that interest in math and science. So I said, okay, I'm going to study math, and we'll see where it takes me. And then in college, I did several internships at JPL, and I just came back home, rode my bike up to lab, and those were really incredible experiences. I think I learned more during a summer at JPL than I would almost an entire semester at college. But it showed me what it means to be an engineer on a day-to-day basis, and kind of showed me what this job is like. And so that really sparked my interest to go then pursue additional schooling and eventually this job at JPL and being part of this team on Perseverance.
Great. And along those lines, what would you tell a high school student today who was interested in becoming an engineer?
I think definitely be your own advocate. So seek out opportunities when you can. Don't hesitate to reach out to people. Everyone has mentors and people they rely on. So if you know someone who's an engineer, or even if you reach out to someone who you don't know, just don't be discouraged. It definitely takes some perseverance to stay with this profession. Also, I'd say it helps to learn some tools that engineers use a lot. So I mentioned Python as a programming language. Nowadays, you can really teach yourself a lot of programming skills just using the internet and like small, low-cost computers. So having that skill set is really valuable. But I think just having an attitude of being persistent and really trying to pursue your dreams is really valuable.
All right, good. That's a good message. Back to the helicopter. Will the helicopter collect any data, or will it be just a "we did it" kind of thing?
The helicopter will collect images, so that's useful data. It'll sort of scout out terrain around the Perseverance rover. But as a tech demo, it's not allowed to be critical to the science of Perseverance. So the Perseverance rover is designed to be successful no matter what happens to the helicopter. We hope the helicopter is successful. And the helicopter will collect images, but and they could be helpful for characterizing the context of what's around the rover, but they're not absolutely needed.
All right, very good. How will NASA's Perseverance rover help us for future human exploration of the red planet?
Cool, yeah. So one of, I think, most interesting instruments on board the rover is called MOXIE. And MOXIE is another technology demonstration of the ability to extract oxygen from the carbon dioxide-based atmosphere on Mars. So if we ever send humans to Mars, that will be an important capability. It's going to be hard to transport enough oxygen to the surface of Mars. What if you could just manufacture it while you're there? And that oxygen is useful for breathing, obviously, if humans were there. It's also useful as part of rocket fuel to get a capsule, back to the Earth from Mars. So if we can show that the MOXIE technology works on Perseverance, you can imagine a larger, more capable version of MOXIE on a future human mission, either before they get there or as part of the mission to manufacture oxygen, which is critical to humans being on Mars.
Right, that'll be an interesting experiment to watch for sure.
Yep.
So, what are some of the biggest challenges to designing a vehicle that can function on a foreign planet? And how is engineering for Mars different from engineering for something that would explore Earth?
Let's see. I think the harsh environment and the fact that you're so far away is really changes the way you think about how you design the vehicle. It really, spacecraft that are around Earth or maybe exploring the surface of the Earth, vehicles that explore the surface of the Earth, you have communication with them and can get in touch if you need to. The rover really needs to be able to take care of itself for extended periods of time, and that impacts all kinds of aspects of the design from the hardware. We mentioned that there's 2 copies of everything, but it also means the software is really pretty complicated. And a large part of my job as a systems engineer and the whole systems engineering team is making sure that the software works in a way that protects the rover when it's by itself on the surface of Mars, a few hundred million miles away.
All right. Now, some questions about the cameras. There are a whole lot of cameras on board. Can you talk about where some of those are located? And do you happen to know any of the resolutions on those cameras?
Okay, yes, let's talk about cameras. So I went back to slide 6 on my own charts here because there are cameras kind of all over the rover. So the easiest ones to spot are the cameras on top of the remote sensing mast, right under mast cam Z. Those cameras are used to take panoramic pictures, and then down below on the front of the rover, kind of between the 2 wheels, are other cameras that are used for navigation and for detecting hazards. The engineering cameras, which are, it's a kind of a broad term for the HAZ cams and the nav cams. I believe the resolution is around 20 megapixels, so it's a huge improvement over what we have on MSL. Also, they're color cameras for the first time. So you have around 4 cameras in the front. On the bottom looking forward, you have cameras on the rear, cameras on the bottom of the remote sensing mast. You have cameras inside the robotic arm, at the end of the robotic arm next to the instruments to provide context for what the instruments are looking at. You have cameras on the descent stage also that are used during EDL. So they're called EDL cams. And this is another really cool aspect of the mission, is that these cameras will take HD video at high data rates. There's one looking up back at the parachute that will see the parachute inflate. There's another one looking down at the rover. So when that sky crane maneuver happens, we'll be able to look down at the rover. And there's one at the rover on the rover looking back up at the descent stage. So that's another part of the camera suite that will really give us it. Well, first of all, it'll be really cool to see all that happen. We don't have exactly that type of data. And also it will be useful for engineers who do the entry and descent and landing systems to see, how does the parachute inflate on Mars? That's a really hard thing to test. It's pretty amazing what these cameras will be able to provide us.
Yeah, it'll be giving us views from all different angles, and it's going to be really neat. And as you said, much higher resolution, even though the stuff we're getting back from Curiosity is really quite good as well.
Yeah.
One last question for you. Who gets to name all the tools on the rover, like Sherlock and Moxie?
So I think the name gets to be chosen by the team that develops the instrument. So each, we have our rover engineering team, but we also have the instrument teams that are equally the instruments are equally complex almost, compared to the rover. So each instrument has its own principal investigator and a whole team of engineers and scientists behind it, and they get to decide on the name. And usually it's an acronym that sounds cool, but also, like, if you unpack it, means something unique and relevant to what the instrument is doing.
All right. Well, thanks again, Matt. Really appreciate your expertise and your time today. I know you are a busy guy. So I'm going to take some more of these questions that are more on the education side of the house and talk a little bit about some of the education activities we have to go along with the Mars 2020 Perseverance mission. And I'll let you get back to your busy day. Thanks again.
Thanks, Oda. Great to be here with you.
All right. So a couple of questions came in about activities for students, and one of those is, will there be any real-time activities for students to conduct here on Earth as Perseverance explores the Martian surface? Yes. We have activities that are going to be simulating the science on the rover, and then the rover science data will eventually be available for students or whoever to process and manipulate. So keep an eye out for those. Also, another question was, will there be a NASA JPL virtual watch party scheduled for the launch? Yes. So I'll talk about that in my very last slide. But for now, let's take a look at some of the education activities that are available on our website. So slide 1 is what you will see if you go to our website. And there is a link there at the top. There are a whole bunch of links at the top. One for intern, learn, teach, news, events. If you click on news, you'll see what is shown in my next slide. This is a teachable moment. We have 3 different types of things in our EDU news. One is teachable moments, which are articles written for teachers summarizing some major event in the news. So the launch is a major event. So it tells you what's going on and why you and your students might care about that and how you might bring that to the classroom, whether it's a virtual classroom you're teaching in or a physical classroom. The other couple of things that are featured under news are Meet the Interns, which are interviews with some of our interns. There are about 10 interviews on there with interns from the Mars 2020 mission. And then there are also teacher features. So we've been asked if there are ways for teachers to explain how they use our resources in the classroom. Yes, we have teacher features. Take a look at those to find some ideas. On slide 3, you will see what you get if you click on Teach from our website, our original website. Teach is a set of standards-aligned STEM lessons for educators. So these are aligned with the Common Core state standards for mathematics and the next generation science standards. So even if you are in a state that does not use those, they're probably useful for you because you are teaching to some sort of academic standards, and a lot of the language is the same. Our activities, you can sort them by the type of activity, the subject, the grade level, the topic, or you can even put in a keyword. We also have a page for students. It's called Learn. And we have, again, different ways of searching for the activities. Some of them are projects that students can do on their own. Some are slideshows, videos, games, even some quizzes in there. And for the learning at home effort that so many of us have been involved in over the past 3 months, we came up with a new website called Learning Space with NASA at Home. On this, you have activities that students can do on their own, along with short, like 2 to 3 minute video tutorials. And those tutorials have subtitles in Spanish. And then we also have FAQs for families that are trying to help their students learn at home. Now, back on the Teach page, we have a whole lot of education resources that are individual lessons. But on slide 6, you'll see our Mission to Mars unit. This is designed as a front to back, learn about Mars, plan a mission to Mars, design your spacecraft, then launch your mission, land on Mars, perform some surface operations, some science, and then a simulated sample return. We put this together in response to a lot of our summer educators and after school educators who were asking for a unified unit for camps and such. So check that out. Slide 7, I have one of my favorite activities from that unit. It is a parachute design activity, and it can be done at any grade level, but we've written it so that it aligns with kindergarten through 2nd grade standards. Students develop a parachute to land a mass of some sort, and they experiment with different shapes, which shape works better than another shape. And they use some math standards to measure and do some geometry and do some timing of their drops. So that's one of my favorites. It's really fun, and it does not require a whole lot of materials. You can use a paper napkin for your parachute. It's really quite flexible on materials. Now, slide 8, this is going to show you one of my other favorite activities of making a cardboard rover. It's called Roving on the Moon as a teacher lesson. We also have it in the student section as Make a Cardboard Rover project. And you use some cardboard, you see some other suggested materials there, but you can use all kinds of different materials. And we give you step-by-step instructions, but we also leave some room for some creative problem solving. So for example, the plans show you using square wheels. Well, square wheels aren't terrible, but there might be something that's better. And of course, you're thinking, well, sure, there's round wheels. Yeah, well, depending on the surface you're on, round wheels might not be ideal. So the idea is students work on the design of the wheels to produce the furthest traveling rover. And there's even a high school extension that involves some physics of that, which is kind of fun. And if you're looking for a bigger challenge, slide 9 shows our on target lesson, which in the student version is called Land a Spacecraft on Target. And as you heard Matt talking, landing on Mars in a targeted area is really tough. The hole-in-one golf example from California to New York is perfect. Now, we're not going to have students trying to hit a golf ball from California to New York, but this activity has students delivering a payload. In this case, we used a little wooden marble. You could use anything. It doesn't have to be a marble. And you run a string between 2 chairs so that one end is higher than the other. And you put a cup that is the spacecraft that carries the marble on the string, and you have to engineer a delivery system so that when the cup slides down the string, and we use a paper clip to help it slide, it will deliver the marble over the target. And that hopefully makes sense of what I'm trying to describe. It is a lot harder to do than you might imagine. So if you have students who like a really good challenge, that's a good one. And we encourage drawing their design and coming up with multiple solutions, coming up with something they want to try, trying it, seeing how it works, modifying it, trying it again. Hardly anyone gets it the first try. So again, simple materials, hopefully things that folks have lying around the house. And you don't even have to use any of the materials we have listed. You could do it with all kinds of modifications. If you don't have a paper cup, that's fine. You could you could fold a paper cone and make it work that way. So all kinds of options. If you have students who are more interested in coding, slide 10 shows you a couple of our coding projects. The top two are Explore Mars with Scratch and Code a Mars helicopter video game. And both of those are using Scratch, or they can use any kind of programming language they want. We just have the steps using Scratch. And on the bottom is if they happen to have robotics at home. Some of your kids have robotics kits. It's a challenge of how to explore the red planet using robots. So they can actually simulate the same kind of engineering and science that we're doing on Mars using their robots that they have either at school or at home. Slide 11 is not necessarily engineering, but sort of engineering because it's computing trajectories and such. This is a lesson called Let's Go to Mars, Calculating Launch Windows. Now, technically, it's calculating launch periods. We named it windows because that's what most people call launch periods. So it's kind of a funny naming convention there. But basically, you heard Matt talk about the fact that we can launch to Mars roughly every 26 months. Well, you could figure out that we're launching in July and then add 26 months, figure out when we could launch again, and you get an approximation. But wouldn't it be fun if you had the opportunity to have your students do the computations from scratch? I think it would be. So this is a lesson that helps students understand how the orbits work, how the transfer orbit works, and helps them understand that if you launch too soon, you're going to miss. Mars will be gone by the time you get there. Or if you launch too late, it's the same problem. You're not gonna land on Mars. You have to do it just right. Well, it's a lot of great math, algebra 2 level, so conic sections, and students can figure out using some string and drawing circles and ellipses and some pretty basic arithmetic that comes along with the algebra 2 work, and they can figure out when the next opportunity to launch to Mars is. So that will answer their questions about why are we launching in July? Why not in December? It's a math problem. And lastly, I'd like to point out to you that all of the images and videos that Matt showed and all of the things that I've shown you are publicly available on our websites. So the Teaching Space with NASA, which is our new teacher page for videos, has links to the images and videos that you've seen in today's program. So look for more information there. There's going to be links to the watch party when it's announced, and you can sign up for all these things as well as joining us for future programs. So our next session, session 3 of the launch conference, will feature science instruments talk, and we look forward to having you join us there. You'll notice that I skipped a few of your questions on the science instruments because I'd love for you to ask those next week. So until then, please have a good time looking over our website and enjoy the activities. And we look forward to hearing your feedback on this program and on our lessons and activities. We'll see you again next time.